talking with Jenni Adams, an astrophysicist from the University of Canterbury.
Astrophysicists want to study the physics of stuff out in space. So people sometimes ask me, about constellations and things. I don't really know any constellations because I'm more interested in actually how the stuff out there in the universe actually works. So I'm going to draw about our project down in Antarctica, which is called IceCube. And IceCube is been built to detect neutrinos. And so I'm going to talk about the objects that we're trying to study and talk about why we want to study neutrinos from those objects. Okay, so we're trying to study the highest energy objects out in space. For example, there can be a black hole. I'll say this is a black hole, and around black holes there's these things called accretion disks, and often you get these kind of jets coming out. That's, we believe, are the most energetic objects. This little thing down here is the Earth. Sometimes we detect these really high energy particles that come in, and we don't really know where they come from because these things are charged. I'll put a little, this means they have electric charge, and when you have an electrically charged particle, if there are any magnetic fields around, they just get twisted around in magnetic fields. So if they come in here like this, it doesn't actually tell us where they've come from, because in the meantime, from wherever they were created, they've gone on these kind of twisty paths. And so there's been a big mystery for about 100 years of we've detected really, really high energy charged particles that have come into us on Earth, but because of this business, we don't know where they come from. What was figured out was that wherever these guys were made, and say they're made in this object that I've got over here, there'll also be these other particles called neutrinos. This is the symbol for a neutrino. Neutrinos made. So the good thing about neutrinos is they don't twist around. They've got no charge at all, so they'll just travel straight from wherever they were created. Many of them will just travel on straight through our Earth and travel off, but every now and then one of them might interact. So we built a big detector at the South Pole. So here is the South Pole, and our detector is under the ground in the ice at the South Pole. And each of these little dots is actually a light detector. So here is a neutrino that did happen coming in, and it did happen to interact at this point. They produce some other particles that produce light, and from this pattern of light we can work out the path that the neutrino has come from. And from the amount of light, so how many of our light sensors picked up the light, we can work out the energy of the neutrino as well. So the idea is that the neutrinos are going to be messengers from this high energy universe, these objects that do travel straight, undeflected, unabsorbed. 5 years ago we discovered that we had neutrinos from astrophysical objects. This was the first time any telescope or any detector had actually detected neutrinos from outer space. Other telescopes, they looked and they saw that our neutrino, actually, let's say it's this one, our neutrino lined up with a blazar that happened to be flaring. So it was in its most energetic state in gamma rays at the same time as we saw our neutrino. So that was in September of 2017 that we found that this neutrino lined up. So we now believe that we have found the first source of high energy astrophysical neutrinos, which was a particular blazar. We've discovered that from these charged particles that we've detected, they're 1 million times more energetic than anything we have ever been able to create on Earth. So nature can make much higher energy things than we can. So if we really want to study the highest energy processes, we have to do the ones out in the universe. And as I talked about, neutrinos are only a direct messenger from the high energy universe.